Assalamualaikum. In the previous session, we had a general discussion about hybridization, what does it mean, and how it may affect the bonding situation in different elements. Today, we will try to explain hybridization with the help of some examples, and we will also discuss some different types of hybridizations that may occur in elements. So, hybridization, as you already know, is the mixing of orbitals to give rise to new orbitals. There are 2 or 3 things that we need to remember before we move on. The first is that hybridization is the mixing of orbitals with different shapes and different energies. And this process gives rise to the formation of new orbitals which have similar shapes among each other, but the shapes are different from the atomic orbitals from which these hybrid orbitals have been produced. Secondly, they have similar energies among each other, but their energies are different from the atomic orbitals formed. Another important thing about hybridized orbitals is that the number of hybridized orbitals that are produced as a result of this process is exactly similar to the number of atomic orbitals that combine to form those hybridized orbitals. Hybridization can be of different types, and it is because of the fact that this process involves the mixing of orbitals of different types. You may have hybridization in which sp orbitals are involved. You can even have hybridizations in which d orbitals are involved. So because of that reason, we can have different types of hybridized orbitals. Their energies would be different, their shapes would be different from each other. So we will discuss the basic 3 types of hybridizations today, and that we will do with the help of at least one example in each. So let's start. The first one is sp hybridization. Now what does that mean? As you can see from the name, this type of hybridization involves the mixing of an s and a p orbital. So if one s orbital combines with one p orbital, it will give rise to 2 sp hybridized orbitals, right? If you remember, in the previous session, we talked about 3 elements, basically boron, beryllium, and carbon. The beryllium, as you know, it belongs to the second group, and if you look at its electronic configuration again, its atomic number is 4. So the electronic configuration is 1s2 and 2s2. And that means that the 2s orbital is complete, and you would expect that it will not form any bonds, but it does form 2 bonds, right? And one of the examples of its molecules is beryllium chloride. So it forms 2 bonds, one each with 1 chlorine atom. So it can attach or it can bond to 2 chlorine atoms through single bonds. Right? Now, how does that happen? If we draw this again on an energy scale diagram, the lowest energy orbital in this case would be the 1s orbital having 2 electrons, and then we have the second shell having the 2s orbital, again having 2 electrons. And as you know that the second shell also has the p orbitals. But in this case, the p orbitals are empty. This is the 2p orbital of beryllium. Now this electronic configuration on this energy scale is the ground state electronic configuration of beryllium. But when it's going to form a bond, and obviously you have to provide some energy. So when you provide energy, an electron will be excited from the lower energy state to a higher energy state, right? So what happens is that one of the electron from the 2s orbital, it jumps into the 2p orbital, in the excited state. So let's see the excited state electronic configuration of beryllium. Now we have one electron in the 2s orbital and one electron in the 2p orbital. It could be in any of the 2p, x, y, or z. This is the 2s. And now you see that beryllium has two unpaired electrons. And now you can expect it to form bonds. So what would you expect next is that the electron in the 2s orbital will combine or will be shared with one electron from one of the chlorines, and this electron in the 2p orbital will be shared with another chlorine atom. But that is not feasible. Why? Because one of the chlorine will come and bond with beryllium through its 2p electron, and the other chlorine will come and bond with beryllium through its 2s orbital. Now both these orbitals have different energies. They have different shapes and they have different energies. And that is why the geometries would be different, the bond angles would be different, and also the strength of the bonds would be different. Beryllium will be forming two bonds with two chlorine atoms, and both will have different energies. That is not feasible in a single molecule. And it has been experimentally proven that the two bonds between beryllium and the two chlorine atoms, they have similar energies. That means that these two bonds have been formed through the overlap of similar type of orbitals from beryllium and the two chlorine atoms. Now to do that, or to get to those similar types of orbitals, what happens is that we have two new orbitals. When this s orbital combines with this p orbital, having one electron each, so you can see that we have two atomic orbitals. So as a result, two hybridized orbitals will be produced. And both these hybridized orbitals will have one electron each. Remember, the energies of these hybridized orbitals will be similar to each other. You can see it on this energy scale. They have similar energies, but their energies are different from the atomic orbitals from which they have been produced. It's different. It is higher than the s orbital, and the energy is lower than the p orbital. They have similar energies among each other. Right? The shapes will also be different. We will discuss that in a couple of moments. Now, these two orbitals are known as hybridized orbitals, but as I told you earlier, that hybridized orbitals may be of different types. And this type of hybridized orbitals is known as the sp hybridized orbitals. This is an sp hybridized orbital, and this also is an sp hybridized orbitals. So in beryllium, we have two sp hybridized orbitals, and these two sp hybridized orbitals will then overlap with orbitals from chlorine to form two beryllium-chlorine bonds. How would their shapes look like? Or how will these orbitals look like? You know that we have a spherically shaped s orbital and we have a dumbbell-shaped p orbitals. When these two combine together or mix together, we will have orbitals with totally different shapes. Now, these sp hybridized orbitals that are produced as a result will have a shape looking like this. Again, you see, it looks like a dumbbell. Looks like a dumbbell of this p orbital. But in the p orbital, this dumbbell has equal sized lobes. The lobes of this p orbital, they are of equal size, but the lobes of this sp hybridized orbital, they are of different size. One of the lobe is larger and the other is slightly smaller. And this is how this sp orbital would look like, or this hybridized orbital would look like. The energies would be similar to each other. They will be different from the p and the s orbitals. Now, how would beryllium form bond with chlorine? And what would be the bond angles? So now we have beryllium with two sp hybridized orbitals, and they would tend to be at maximum distance from each other. So to have maximum distance from each other, they must be at an angle of 180 degrees from each other. And then we have the two chlorine atoms coming from here, forming bonds with this sp hybridized orbitals of beryllium. And that is how beryllium chloride is formed. So, the overall geometry of beryllium chloride would be linear because it has two sp hybridized orbitals and they have to be at maximum distance from each other. And this is how beryllium forms two bonds with two chlorine atoms, one with each chlorine atom. And this is the type of hybridization which we call sp hybridization, in which one s orbital combines or mixes with one p orbital to form two new orbitals, which are known as sp hybridized orbitals. Now let's see another type of hybridization that is known as sp2 hybridization, or the sp2 hybridized orbitals. So as we saw in sp hybridization, one s orbital combines with one p orbital. That is why it is known as sp hybridization. If in a case one s orbital combines with two p orbitals, then we call it sp2 hybridization. And because we are mixing one s with two p orbitals, that means we are mixing three orbitals. So when you are mixing three atomic orbitals, as a result, you will have the formation of three hybridized orbitals, which we call the sp2 hybridized orbitals. An example of this would be boron. So boron belongs to the third group, and the electronic configuration is 1s2, 2s2, and 2p1. It has 5 electrons, and the valence electron, the last electron, goes into the 2p orbital. Now, let's see again the energy diagram of boron. So we have the 1s orbital here having 2 electrons, that is the 1s. Then we have the 2s orbital, again having 2 electrons. And then we have the 2p orbital. Now in this case, the 2p orbital has 1 electron, and that will get placed in any of these 3 x, y, or z orbital. And this is the ground state electronic configuration of boron. Again, when boron tries to form a bond, or when it is about to react, it needs energy. And when you provide it energy, an electron will be excited from the 2s orbital into the 2p orbital. So what happens is that one of these electrons jumps into one of the empty, the vacant 2p orbitals of boron. So let's see the excited state electronic configuration. So what happens in the excited state is that one of the electrons gets excited to the 2p orbital, and now we have an unpaired orbital, an unpaired electron in the 2s and 2 unpaired electrons in the 2p orbitals. And now it is going to form a bond. It has 3 unpaired electrons. And so now you can expect that it can form 3 bonds. But one of its bonds will be formed through the 2s orbital, and 2 bonds will be formed through the 2p orbitals. And again, there will be a problem of bond angles and bond energies. And so again, if we consider hybridization, what happens is that this s orbital mixes with these 2p orbitals to form 3 new orbitals. Now, because we are mixing one s with 2p orbitals, we will have 3 hybridized orbitals as a result, and the total number of electrons present in these s and p orbitals is 3. So the 3 sp2 hybridized orbitals will also have three electrons, one in the each hybridized orbital. This is an sp2 hybridized orbital. This is an sp2 and this is sp2. So we have three sp2 hybridized orbitals. Again, the energies will be similar to each other, but different from the p and the s orbital from which they are produced. And the shapes will also be different. Again, the s is spherical orbital, p is a dumbbell-shaped orbital, but these sp2 hybridized orbitals will have similar shapes just as we discussed for sp hybridized orbital. It will be looking like a dumbbell, but with lobes of different size. Let's see how boron will form bonds. So boron now, you can see that it has three hybridized orbitals, which we call the sp2 hybridized orbitals. And these three orbitals would like to be at maximum distance from each other. They would tend to be at maximum distance from each other. And to do so, they will have an angle of about 120 degrees. If you consider this as a full circle, and you divide, this full circle has 360 degrees. If you divide 360 by 3, it's equal to 120 degrees. So the angle between these two orbitals will be 120 degrees. This will be 120 degrees. And this will also be 120 degrees. Now, it can form bonds with three other atoms. So an example of is BF3. So if boron has the availability of three fluorine atoms, it will form bonds with three fluorine atoms in such a way in which each fluorine is bonded through a single covalent bond with boron, and the bond angle between them will be 120 degrees. And so in the previous case, in case of beryllium chloride, we saw that the angle was 180 degrees. The overall geometry was linear. Now this is not linear, it's a trigonal geometry. Because the angle now is 120 degrees. Right? So this is an example of sp2 hybridization. Let's see the third type. The third type of hybridization is sp3 hybridization. So if one s orbital combines or mixes with three p orbitals, we will have the formation of four sp3 hybridized orbitals. Because we are mixing four atomic orbitals, one s and three p. So as a result, we will have the formation of four sp3 hybridized orbitals. An example of this is that of carbon. The carbon has an electronic configuration 1s2, 2s2, and 2p2. The lowest energy orbital, the 1s, has 2 electrons, and then the higher energy orbital, 2s, has 2 electrons, and then we have the 2p orbital, which has 2 electrons, 1 in the each of the orbitals. In carbon, if it is going to form a bond or it is going to react, you have to provide energy. And so one of the electrons will jump from the 2s orbital into the vacant 2p orbital. So this is the ground state electronic configuration of carbon. Let's see the excited state configuration. This is the 2s orbital, now having 1 electron, because one of it is excited to the 2p orbital. X, Y, and Z. And now carbon has 4 unpaired electrons. But again, just like in the previous examples, it cannot form 4 bonds, 1 through the s and 3 to the p through the p orbitals. So what happens is that this s combines with the 3p orbitals to form 4 sp3 hybridized orbitals. The number of electrons in both s and p is 4. These sp3 hybridized orbitals will also have 4 electrons, they will be singly filled in these 4 orbitals having similar strength, right? This is sp3. These sp3 hybridized orbitals will also have similar shapes to each other, just like the dumbbell we discussed in the previous examples, and they will have similar energies among each other, but the energies and shapes will be different from the p and the s orbitals or the atomic orbitals from which they have been produced. An example of molecules in which carbon is sp3 hybridized is that of methane. So what happens in methane is that carbon forms 4 bonds with 4 hydrogen atoms. Hydrogen, you know, it has a 1s orbital having 1 electron. So these 4 hybridized orbitals again would tend to be at maximum distance from each other. And to have maximum distance from each other, they will tend to have an angle of 109.5 degrees from each other. So each of these orbitals has an angle of 109.5 degrees between them. And now these 4 sp3 hybridized orbitals will overlap with the 1s orbital of hydrogen to form 4 single covalent bonds, and the overall geometry would be tetrahedral. You have a bond angle of 109.5 degrees, and you have maximum distance between these 4 hybridized orbitals. The geometry would be tetrahedral. So this methane molecule has a tetrahedral geometry. But carbon is an atom that can have different types of hybridization. Even other elements can also have different types of hybridization. Carbon can have sp3 hybridized orbitals, it can have sp2 hybridized orbitals, or it can also have sp hybridized orbitals. An example of molecule in which carbon is sp2 hybridized is that of ethene. You must have heard about alkenes in which carbon is double bonded to another carbon, and that is where carbon is sp2 hybridized. So in that case, one s orbital mixes with 2 p orbitals to form 3 sp2 hybridized orbitals, leaving behind 1 unhybridized p orbital. And that unhybridized p orbital is then involved in the formation of the second bond, the pi bond between 2 carbon atoms. And that is why we have a double bond between 2 carbon atoms in case of molecules in which carbon is sp2 hybridized. It can also have sp hybridization. In that case, 1s mixes with 1 p orbital, leaving behind 2 unhybridized p orbitals. So we have 2 sp hybridized orbitals forming sigma bonds, and these 2 unhybridized p orbitals would then form 2 pi bonds. So a carbon that is sp hybridized usually forms triple bonds. An example of that is alkynes, in which carbon is triple bonded to another carbon. But you can have carbon dioxide as an example, in which carbon again is sp hybridized. It is bonded to 2 oxygens on both sides, and that is why carbon is sp hybridized in carbon dioxide. Right? So this was about different types of hybridizations. So I hope you've got it. Thank you so much.